After we have seen first law of electrolysis, now we want to talk about the Faraday's second law of electrolysis. Here, for the last period, we learned about the first Faraday's law, and we said it's all about the same electrolytes. But here, we have to consider about electrolytes, different electrolytes. They may be 3, 2, 4, and 4, and whatever it is. But we consider about different electrolytes. Now, Faraday's second law of electrolysis states that when the same quantity of electricity, means the quantity of electricity is the same, and it is passed through solution of electrolytes, of different electrolytes. Not one electrolyte, of different. Different electrolytes. Is passed through the solution of different electrolytes. The mass of the substance liberated or deposited at the electrodes are very proportional to the chemical equivalents. Not electrochemical equivalent. We have electrochemical equivalent and we have chemical equivalents. Electrochemical equivalent is constant for the particular elements, as we have seen in the first Faraday's law of electrolysis. But once you are talking about the Faraday's second law of electrolysis, we are just talking about chemical equivalence. Electrochemical equivalent is abbreviated as letter Z. That is what we have seen. But chemical equivalent is abbreviated by letter E. So the second Faraday's law of electrolysis states that when the same quantity of electricity is passed through the solution of different electrolytes, maybe we may have silver chloride and also we may have copper 2 sulfates. These are the two electrolytes. So we may use the silver chlorides to deposit the silver, and also we may use copper sulfate to deposit the copper. But the quantity of electricity that is passed here is the same. Means the quantity of electricity must be the same. Means Q, that is quantity of electricity, is constant for every electrolyte. But what is different is electrolytes. Now, that is, we say, when the same quantity of electricity is passed through the solution of electrolytes, of different electrolytes, the mass of the substance liberated or deposited at the electrodes are direct proportional to the chemical equivalent. Mathematically, that was how we say, but mathematically, we have something to talk about here. Now, mass of the substance is direct proportional to the chemical equivalence. Now, where M is mass of the substance and E is what we call it chemical equivalence. Now, the mass of the solution, the mass of the substance deposited will be direct proportional to the chemical equivalent of the substance. Now, that is, to remove the proportionality constant, mass is equal now to quantity of electricity times the chemical equivalent. Why is it quantity of electricity? Because it is the one which is constant. Now, this is what we can say from the second Faraday's law. But at different electrolytes, for the first electrolytes, mass 1 is equal now to quantity of electricity times E1. And the mass 2 also is equal to this one, is equal to quantity of electricity, then this is E2. Now this is for the first electrolytes and this is for the second electrolytes. You may see there is no variation of quantity of electricity. There is no variation of quantity of electricity. Why is it so? It is very simple. It is simple because we're talking about, we have said for the same quantity of electricity, means quantity of electricity is the same. Now, once you find the ratio of the two equations, means you'll be having M1 over M2 is equal now to Q E1 over Q E2. But mathematically, these are like terms. They cancel each other. It is where now you have, it is M1 over M2 is equal now to E1 over E2. So this is according to the second Faraday's law of electrolysis. Because it is variable and it is valid once you use different electrolytes. As I said here, if now you are having the electrolyte of silver chloride and the electrolyte of copper 2 sulfate, means that you are just talking about two different electrolytes. But the quantity of electricity that is passed through them, you may have, this is the first electrolyte and this is the second electrolyte. Now, the current of electricity that is passing here and the quantity of electricity that is passing here is the same. Means you have to contact the same time that was taken to for the current remaining electrolytes and also the same time that was taken here for the current remaining into electrolytes. Therefore, this is the formula that is developed. Once now you're talking about different electrolytes, this is the formula that we use. But how do we obtain what we call it chemical equivalence? Now the chemical equivalent is taken by looking at the relative atomic mass of an element and its valence or charge, and it is the charge. We prefer to use charge here because we are just talking about ions or valence. Therefore, if now you are looking for the chemical equivalent of aluminium, the relative atomic mass for the aluminium is 27 and it is the charge is 3, and that is why chemical equivalent for aluminium is 9. The same applied if now you are looking for the chemical equivalent of copper. Now remember, the relative atomic mass for a copper is 64 and also it is the valence or charge is 2. Now the chemical equivalent for copper is 32. So you got to be very careful. This chemical equivalent is calculated by using this formula, but electrochemical equivalent is not calculated. It was determined experimental and it is constant for the particular element. But the chemical equivalent is also constant for the particular element because it depends on the constant, what we call the relative atomic mass, and it is the charge. There is no variation in the charges of the elements. If now you're talking about aluminium, you won't find aluminium with 2 charges and 3 charges. No, it's the same thing. If now you're talking about copper, you won't find copper with 1 charge and 2 charges. No, it is the same thing. But it is calculated under this formula that is the chemical equivalence is equal now to relative atomic mass of an element of a charge or valence of an element. And that is why I've given you an example. If now you're talking about chemical equivalent of aluminium, we have relative atomic mass of aluminium 27 and we have what we call it the charge of aluminium, which is positive 3, and then we divide, we get it is 9. The same applied if now we're talking about chemical equivalent of copper, we have 64 as relative atomic mass, and also we have 2 as a valence of what we call it copper. Now we have that 2 as copper, and also we have 9 for what we call it aluminium. So first of all, you have to know how you can determine the chemical equivalence for the particular elements. And then so far you may compare. But this law is very important when now you are talking about different electrolytes with the same quantity of electricity that is passing through different electrolytes. As I said before, that we may consider the silver chlorides as an electrolyte and copper 2 sulfate as an electrolyte. But both of them, the quantity of electricity is the same, but different electrolytes. Now, the electrolytes of silver chloride may deposit what we call it silver, and the electrolytes of copper 2 sulfate may be used to deposit what we call it copper. So, we are just deposition. We are just looking for amount of different substance, silver and copper with different electrolytes, but the current and the time that was taken in the electrolytes for the electric current to remain in the electrolytes is the same, and that's why we represent about the same quantity. Now let us see an example on how we can use this second law and where we can apply and how we can apply different examples. Now let us see the second example. Let us see the example for the second laws of electrolysis. The second Faraday's law of electrolysis. A current of 10,000 ampere is passed through an electrolytic cell for purifying copper for 12 hours. For 12 hours. That is, the current was equal now to 10,000. This took time of 12 hours to remain in the electrolytes so as to purify what we call it, copper. Now, the copper was purified for 12 hours for the current to remain in electrolytes. Now, the current of 10,000 ampere remains in the electrolytes to purify copper for 12 hours. So means that the current spends 12 hours to remain in the electrolytes so as it may purify what we call it copper. Then the question, what is the mass? The pure copper, the mass of the pure copper that is deposited at the cathodes. Therefore, because you are just talking about the copper only, and it was purified from maybe copper sulfates, because we have not been taught, as a single electrolyte, we use the first Faraday's law, that is M is equal now to Z IT. Now, for the first question, it was all about the first Faraday's law. Remember, we've been given Z is equal now to 3.29 times 10 power negative 4 times current is 1,000. It's 10,000. Now times time. Remember the time that we've been given here. It is in terms of hours. So 12 times 60 times 60. Why is it so? Once you multiply by 60, for the first time you obtain minutes. Then you multiply once again for the 60 to obtain seconds. Because what we have to know, 1 hour is equal now to 360. This one, seconds. This is what we have said. So we use this principle to convert hours into seconds. So in short, we multiply it by 6 for the first time to obtain minutes, 6 for the second time to obtain seconds. So this is converted. No matter we're talking about 24 hours, we have to convert them into seconds. And that is why now it is by 12, it is now by 60, it is now by 60. So mathematically, this is Z, here it is. And this is the I, here it is. And this is the time, here it is. We are looking for the mass. It is therefore now we get what we call it is 1.42 times 10 power 5 gram. This is the gram. So the mass that is obtained here, mass is equal now to 1.42 times 10 power 5 gram. Once you have multiplied, you obtain this is what we call. So this for the first question. But for the second question, what is the mass of aluminium would be deposited if the cell was changed to refine aluminium? Now, you are just talking about the copper and aluminium. So now we are just talking about two different electrolytes. Now, for the second question, you have to use the second Faraday's law of electrolysis. Now that was B. Now B, we have to know from mass 1 over mass 2 is equal now to E1 over E2. But E1 is the one for the copper. Therefore, now if now you're talking about B, you are talking about the copper and you are talking about aluminium. So we have E of copper, relative atomic mass of copper is 64 over valence or charge, it is 2. And here, relative atomic mass, relative atomic mass of aluminium 27 over which is 3. And we've been given. Now, relative atomic mass of copper over this one. Because I said chemical equivalent, not electrochemical equivalent. Chemical equivalent is equal to relative atomic mass over charge, over its charge, or what we call it valence. Now, once you look at you looking. Now let us go for the copper is E1 and for the aluminium is E2. Now here we have 32 as E1 and here we have E2 which is equal now to 9. So this is we have. Therefore, remember we have referred or we have considered the copper as the first amount that was produced. Also, it is mass. The first mass, here it is. Therefore, we have that one, which now we may even try to convert it into kilogram, because it is not a risk for us for the second law to deal with kilogram. Now, mass 1 will be equal now to 142. That is now once it is this one kilogram. So this one times 10 power 5. Now, which is now we can say it is 142 kilogram. Now, for the mass, the first mass is equal now to 142 kilogram. This is converted to kilogram. Therefore, from the second Faraday's law, we have M1 over M2 is equal now to E1 over E2. This is how we use it. The first mass is 142 over the second mass we don't know. It is what we've been asking. But the chemical equivalent for the copper, we have seen it is 32. And that of aluminium is 9. Now we are looking for the value of M2. You cross multiplication. Now we have 32 M2 is equal now to 142 times 9. Therefore, you divide by 32, you divide by 32. It is therefore now we are looking for the second mass is equal now, it is 4.280 kg. Here it is. Now the mass of aluminium that would be deposited if the cell was changed to refined aluminium is 40.28 kg. Why is it so? As I said before, if now you are talking for a single electrolytes, kama ni electrolytes ni moja, basi we use the first Faraday's law, which now M is equal now to ZIT. But once it is referred to different electrolytes, we use now the second Faraday's law, because this is applicable. Because whenever you're talking about second Faraday's law, it is applicable for a different electrolytes having the same quantity of electricity. Now, the quantity of electricity that was used at the copper to deposit copper and the quantity of electricity that was used to deposit aluminium, it was the same. But electrolyte that was used to deposit aluminium and copper are a difference. This may be deposited from copper to sulfate, this may be deposited from aluminium sulfate and so forth. But these are the electrolytes, are different electrolytes. But they are having the same quantity of electricity that is passing through those electrolytes. And that is why it is applicable. The second Faraday's law, it is applicable to the second equation solving it, because we are just talking about different electrolytes, but they are having the same quantity of electricity that was passing through the different electrolytes. So it is very important for us to understand, for the first equation, we are just talking about first Faraday's law. And for the second equation, we are just talking about the second Faraday's law, because we're talking about different electrolytes. So whenever you are dealing with word problems concerning about this Faraday's laws of electrolysis, you have to understand there are differences. And the differences that are, the first one is dealing with the same electrolytes. But the second one is dealing with different electrolytes. But these different electrolytes, they are having the same quantity of electricity that is passing through them. So you have to understand. Now, this is the end of what we call it the second Faraday's law. And now we thank you very much for watching our channel.